Hello everyone, and welcome back to another StudyShed video. In this video, we'll be taking a look at the topic of limits and limit properties. Let's get started. So first off, what is a limit? In its simplest form, a limit is the value a function takes as the input approaches a certain number. In a more mathematical definition, a limit is the value a function f of x takes as x gets arbitrarily close to a value from both sides. A limit, however, does not concern with what happens at the value, just only on either side of the value and as x gets arbitrarily close to that value from both sides. So now we have a visual example over here. We'll take a look at this graph. In this case, we can claim that the limit as x approaches c from both sides is f of c. In its purest form, this is what a limit is. It is the value a function takes when x gets closer and closer from both sides to a number c. And this is here I should introduce a slightly different view of looking at it. And this is because f of c and the limit as x approaches c of f of x are two completely different things. If f of c in this graph were defined to be 1, the limit as x approaches c of f of x would still be f of c. So make sure you know that distinction. So how would we evaluate a limit? For a limit to exist at a value c, two conditions must be met. First condition, the function must approach a real number as x approaches c, both from the left and from the right. And 2, the value of these two approaches, which we call it mathematically a one-sided limit, must be the same. If these two conditions are met, we can write, in mathematical notation, the limit as x approaches c of f of x is equal to L, where L is a real number. Here we're going to go over an example using a table. So here's a table of values for some arbitrary function f of x. We can see that f of 0.99 is 1.9999. F of 0.999 is 1.9999999. We don't know what f of 1 is, and we know that f of 1.001 is 2.0000001, and f of 1.01 is 2.0001. So from this table, you should take a stab at what the question is trying to ask, and in its most purest form, we could say that this table is trying to get us to find the value of f of 1. However, in this case, we are actually trying to find the value of the limit as x approaches 1 of f of x. And as I just stated, that is what the question is trying to ask. So how will we go about doing this? So we can take a look at the table, and we can say, claim that the function f approaches 2 as x approaches 1 from the left. As you can see, as we add more and more 9s to 0.99, we can see that this number on the left, 1.999 and 1.999, gets larger and larger, and it goes towards 2. And when x approaches 1 from the right, the same things. The numbers slowly reduce, getting closer and closer to 2. So you can claim that the limit from the left is 2, and the limit from the right is also 2. And by our definition of a limit that we just developed in the last slide, you can say that the value of the limit as x approaches 1 of f of x is 2. So now, what are some limit properties? We don't want to always rely on a graph when we're evaluating limits, so there are some easy properties that we can use. So first off, let's define two limits. We have the limit as x approaches c of f of x is equal to some real number c, and the limit as x approaches c of g of x is equal to d. Note that when we write this implies that their one-sided limits are equal. So if these two things are true, then we have 5 different limit properties. So our first property is that of a composite function, the limit as x approaches c of f of g of x. So the limit as x approaches c of f of g of x is f of the limit of g of x. So we take the limit as x approaches c of g of x, and whatever that value is, we plug that into f. So if the limit of g of x was 2, then we would find f of 2. And if the limit as x approaches c of g of x was d, then we'd find f of d. And in this case, we don't know what f of d is, but I digress. Our second property is the limit as x approaches c of f of x plus g of x. And what our limit property allows us to do in here is allows us to split the limit into 2, saying that we can take the limit as x approaches c of f of x individually, which we know is c, and the limit as x approaches c of g of x, which we know is d, and then add their two values. So we can say that the limit as x approaches c of f of x plus g of x is equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x, which we know is c and which we know is d, and we just add them to get c plus d. The exact same property works for subtraction and multiplication. So going down one by one, we say that the limit as x approaches c of f of x minus g of x is c minus d, and the limit of x approaches c of f of x times g of x is c times d. And now division. While the property may seem to look the same, we should also know that c and d are real numbers, so it's highly possible that c and d can both be 0. This is something called an indeterminate form. And we'll go over that next, but note that even though it follows the same property, that we can split the limits, say limit as x approaches c of f of x and limit as x approaches c of g of x, evaluate them separately, and then combine the result. This result of 0 over 0 is very possible. So an introduction to indeterminate forms. As I just mentioned before, when we're evaluating quotients for limits, we could end up with something known as an indeterminate form. And these are numbers that don't have clearly defined values. Two very important examples that you will see a lot are 0 over 0 and infinity over infinity. And while it may seem 0 over 0 and infinity over infinity are undefined, when you evaluate limits, you'll find out they actually take multiple possible values. 0 over 0 is not 1, infinity over infinity is not 1. They can be 1/2, 2, and so on. And this is because in the case of 0 over 0, well, that's just straight confusing and undefined. Not really undefined, but we just say it's indeterminate. However, infinity over infinity is the more curious example, because if you take a really large number and divide it by a really large number, that should be 1, right? However, in this case, the two infinities are not necessarily the same thing. We have the limit as x approaches infinity of x squared and the limit as x approaches infinity of x. The x squared is way larger than the x, as we know from the graph. So this shouldn't be 1, right? And we'll go over exactly how to evaluate such limits later. And a general idea to get rid of indeterminate forms, you must use one of the limit techniques, which you'll discuss next, to get rid of them before directly evaluating the limit by plugging in the number. So limit techniques. We have 6 techniques to evaluate limits. And for all of these techniques, we approach that x approaches a real number c or infinity for to use all these techniques. So our first technique, which we know as direct substitution, states the following. If f is defined at c, let's simply substitute c into f of x. F of c is the value at this limit. This is only true if when you know the graph is continuous or exists for all real numbers and it doesn't jump around anywhere. Like there's no holes. If you take like y equals x, then if you plug in 3, then y doesn't equal 5, something like that. If the graph is a smooth line, then you can use this technique. This is also the same technique as taking a limit from the left and the right and seeing if they're equal. This is exactly what direct substitution is. Our second technique is to attempt to factor and cancel any like terms from the argument of the limit. So in our case of x squared over x, x is common in both the numerator and the denominator. So we can cancel out the x. And since we know x can't equal 0 because it would make the function undefined, this cancellation is perfectly valid. After we cancel, we can then plug in c into f of x. Our third technique is quite similar to our second technique, and this is to rationalize the argument of the limit by either, let's say if we have a square root, we either multiply it by itself or we multiply by a conjugate, which is really common when we're evaluating trigonometric limits. Our fourth technique is to divide our individual terms by a factor of x. And this may seem confusing, but we'll go over it, and this is very common for limits that approach infinity. Our fifth technique is to use one of the 2 trigonometric limit identities, which we will go over next. And our sixth technique is the squeeze theorem, which we will also discuss next. And notice, for those who might be reviewing, L'Hopital's rule is not mentioned here, and that is because that is a completely different limit technique that revolves around the concept of the derivative. So we'll go over that in a completely different video. So, trigonometric limits. There are 2 key trigonometric limit identities, and here are the 2 of them. Our first one is the limit as x approaches 0, sine x over x equals 1. And the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. These 2 are very commonly used and are very fundamental to know. We will not prove them in this video, but if people are willing or wanting a proof, that we will do it. Again, be sure to know these as they are very useful. And next we have the squeeze theorem. The squeeze theorem states that if f of x, g of x, and h of x are functions defined over the same interval, and f of x is always less than or equal to g of x is always less than or equal to h of x for all x in the domains of f, g, and h. If limit of x approaches c of f of x is equal to the limit as x approaches c of h of x, which is equal to L, then the limit of as x approaches c of g of x is also equal to L. So what does this mean? Let's take a graph. Suppose this blue function over here is f of x, the red function is g of x, and the green function is h of x. we know that the green function is always greater than the red function, is always greater than the blue function. Now, as you can see from the graph, the green function and the blue function both tend to approach 1, and the red function is always in between the two. As you can see, because the red function is always between the two, and the blue function and the green function both approach the same value, we know since the red function is always in between, it has to approach the same value. And this is what the squeeze theorem is saying. If you have two functions, and a third function that's always in between those two functions, if the two main functions that you know approach the same value of the limit, then the third function should also have the same value as the limit. And going back to our example, our mathematical statement, we say that the limit as x approaches c of f of x is equal to the limit as x approaches c of h of x is equal to L. And if we were able to graph that, then it makes it obvious, since g is between f and h, that we know that also has to equal L. So infinite limits. So you could have a scenario like this. The limit as x approaches infinity of f of x equals L, and the limit as x approaches c of f of x equals infinity. So what do these two scenarios mean? In our first scenario, the function is getting closer and closer to some value as x grows larger and larger. This is a sign of a horizontal asymptote. As you can see from a graph, as we get larger and larger, a common example of this is 1 over x. As x gets larger and larger, the value of f of x equals 1 over x gets closer and closer and closer to 0. And this is our asymptote. In our second scenario, the function is going larger and larger as x gets closer and closer to a certain value. This is a sign of a vertical asymptote. And another way you can think about this is also using the function f of x equals 1 over x. As x approaches 0, from the right side and perhaps the left side as well, you notice that the quantity 1 over x, if you plug in smaller and smaller numbers, that quantity becomes larger and larger. And in that case, we say it tends to infinity, or negative infinity, depending on the side you take the limit from. So now we're going to go over examples of evaluating limits with each method. So our first method is direct substitution. The question asks to find the limit as x approaches infinity of x minus 3. So this may seem pretty confusing as, oh no, there's an infinity. But this is still an example of direct substitution, because x minus 3 is a function that exists for all real numbers, and infinity is a pretty large real number. And so if we plug in an extremely large number, we subtract 3 from it, that's still going to be an extremely large number. And so we claim that the limit as x approaches infinity of x minus 3 is just infinity. Our second technique would be factoring and canceling, and our limit in this case is the limit as x approaches 3 of x minus 3 over x squared minus 9. First, we'll try direct substitution, and when you plug it in, it takes the curious form of 0 over 0, as when we split the limit into 2 using our quotient property, we take the limit as x approaches 3 of x minus 3, which is 0, and the limit as x approaches 3 of x squared minus 9, which is 0. So, taking the indeterminate form of 0 over 0 gives us a hint that we might need to factor or rationalize. So factoring and canceling like terms gives us the following. So we notice that in the denominator, x squared minus 9 is a difference of two squares, and we can factor using the property that a squared minus b squared is equal to a plus b times a minus b. And notice that's what we've done. We split up x squared minus 9 into x minus 3 and x plus 3. And so as you know, over the domain of this function, x can't be 3. It is perfectly allowed to cancel out the x minus 3's from both the numerator and the denominator. Now we are left with the limit as x approaches 3 of 1 over x plus 3, and we split this into two limits. We take the limit as x approaches 3 of 1, which is just 1, and the limit as x approaches 3 of x plus 3, which is 6. Combining our answer, we get 1/6. The other way you could do this is just directly substitute in 3 to 1 over x plus 3, and you get 1/6. Third method, we have rationalization or multiplying by a conjugate. So we have the limit as x approaches 0 of 1 minus cosine x over sine of x. Using our limit properties and directly plugging in first, obviously go for direct substitution first. That is the number one technique when evaluating limits. We plug in 0 to 1 minus cosine x, we get 1 minus 1, which is 0. And we plug in 0 to sine x, which is 0. So we get 0 over 0, which gives us a hint that we need to factor or rationalize. In this case, there's really nothing to factor, as 1 minus cosine x and sine x don't really share any common factor. So we're kind of stuck here. But the term 1 minus cosine x gives us a clue that we might want to multiply by the conjugate 1 plus cosine x, as we have a very common trigonometric identity, sine squared x plus cosine squared x equals 1. And we could manipulate that to get 1 minus cosine squared x equals sine squared x. And here we have a 1 minus cosine x, so we want to multiply by 1 plus cosine x to get the top into 1 minus cosine squared x. So that's what we've done here. We multiply both the numerator and the denominator by the same amount, And we have to do this because we want to make sure this quantity maintains equality. So whenever you multiply the limit by something, you always want to make sure that the value of the quantity doesn't change. So if you have if you have like limit as x approaches 0 of x, if you multiply the x by 2, you also have to divide it by 2 to maintain equality. And that's what we're doing here. When we completely simplify our limit expression, we get 1 minus cosine squared x over sine x times 1 plus cosine x. Using our trig identity, we get sine squared x over sine x times 1 plus cosine x. And since we know that sine x can equal 0, which means x can equal 0 in the domain of this function, we are perfectly allowed to cancel out the sine x's, leaving us with the limit as x approaches 0 of sine x over 1 plus cosine x. Using our limit properties, we split the limit into 2, and we get limit as x approaches 0 of sine x, which is just 0, and the limit as x approaches 0 of 1 plus cosine x, which is 2, but 0 over 2 is just 0, and that is our answer. 4. Division by a power of x. Find the limit as x approaches infinity of 3x squared over x squared plus 3. And this, we have to understand something known as the dominating term. What a dominating term is the term in a polynomial that affects the function the most. In this case, for the numerator, it would be x squared, and the denominator, it would also be x squared, because those change the function the most. Since the numerator and the denominator have the same dominating term, we'll claim that x squared is the dominating term for this entire rational function. So, to maintain equality while allowing our limit to be evaluated, we can divide every term by x squared, as in this case we're just removing an x squared from the value. And notice we have to do this because if we plug in infinity into the function, we get infinity over infinity, which is indeterminate. So if we divide every term by x squared, we get the limit as x approaches infinity of 3 over 1 plus the quantity 3 over x squared. And notice, this is not in the indeterminate form of infinity over infinity anymore, so we use our limit properties to split the limit into the limit as x approaches infinity of 3 over the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 3 over x squared. The first two limits, the first one in the denominator and the numerator, both evaluate to 3 and 1. But what about the last one? In limit as x approaches infinity of 3 over x squared, 3 is being divided by a really large number. If you start dividing 3 by larger and larger numbers, this quotient gets closer and closer to 0. So we'll claim that the limit as x approaches infinity of 3 over x squared is 0. So now, simplifying your answer, we get 3 over 1 plus 0, which is just 3 over 1, which is 3. Our fifth technique, which in this case we want to find the limit as x approaches 0 of sine 2x over x. And notice, we went over a trigonometric limit identity, which is the limit as x approaches 0 of sine x over x equals 1. But however, we have a 2x over here, so we want to make it in the form sine x over x. Essentially, we want the argument of sine and the denominator to have the exact same value. However, in this case it isn't. We have to somehow turn this x into a 2x. So we multiply that bottom by a 2. However, to maintain equality within the argument of the limit, we have to multiply the numerator by 2 as well, giving us the quantity, the limit as x approaches 0 of 2 sine 2x over 2x. We can pull out the 2 from the argument of the limit because using our limit properties, we know that limit as x approaches 0 of 2 is just 2. So we get 2 times the limit as x approaches 0 of sine 2x over 2x. However, it's not in the form sine of a variable over a variable because 2x and 2x are not x and x. So we're going to make a substitution. Let u equal 2x. Now what happens as x approaches 0? If you take the limit as x approaches 0 of 2x, we get 0. So the limit as x approaches, or the limit as u approaches 0 should also be 0. Because as 2x approaches 0, u approaches 0. So we can rewrite this limit as the limit as u approaches 0 of 2 sine u over u, which is the limit as u approaches 0 of 2, times the limit as u approaches 0 of sine u over u. Limit as u approaches 0 of 2 is just 2, and by our definition, the limit as u approaches 0 of sine u over u is 1, so 2 times 1 is 2. Finally, we have the squeeze theorem. We want the limit as x approaches 0 of x times cosine 1 over x. So first off, this limit doesn't really seem to follow any of our other examples here. But we do know that for any cosine function, cosine nx, where nx is a polynomial, we know that cosine, whatever, in this case, 1 over x, has to be between negative 1 and 1, because the definition of cosine. Thus, we can claim that the cosine 1 over x is in between negative 1 and 1. Now, we can multiply both sides by x. So you get negative x is less than or equal to x times cosine 1 over x is less than or equal to x. And notice we have our three functions here. We know the domain of x, we know the domain of negative x, and we don't really know the domain of x times cosine 1 over x. However, if we take the limit of all three sides of this inequality, now we know the value of the limit of negative x and x as x approaches 0, which you both know is 0. And since they're the same thing, the function in the middle also has to approach that value by the squeeze theorem. So you know the limit as x approaches 0 of x times cosine 1 over x is 0. And that's limits for you. Hopefully that video wasn't too complicated. In our next video, we'll be going over continuity and the intermediate value theorem. Thanks for watching, and happy studying.